The Webb looks so far out that it's capturing light that's been traveling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. For the most distant galaxies, we're looking back in time almost to the Big Bang. The vastness of the cosmos may appear boundless, but all of it originated from what we refer to as the singularity. Presently, this constitutes our understanding of the Big Bang theory. However, the James Webb Space Telescope, JWST, has uncovered profound secrets about the birth and evolution of the universe, leaving us astounded. Renowned physicist Brian Cox has declared that the remarkable discoveries made by the JWST could potentially reshape our comprehension of the universe as a whole. Join us as we delve into these recent celestial revelations that promise to revolutionize our understanding. The James Webb Space Telescope, named after the distinguished NASA Administrator James E. Webb, stands as a marvel in modern astronomical exploration. This telescope represents a significant technological leap forward from its predecessor, the Hubble Space Telescope. Resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST exceeds the capabilities of its forerunner. It employs cutting-edge technology and a design optimized for studying the cosmos in unprecedented detail. Unlike the Hubble, the JWST delivers clear and sharp images of distant celestial bodies, operating primarily in the infrared spectrum. This unique feature allows it to penetrate cosmic dust and capture celestial objects that were previously hidden from our view. With its colossal 6.5-meter primary mirror composed of 18 hexagonal segments, the JWST dwarfs the Hubble's mirror in size. Positioned approximately 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in sync with Earth, ensuring a stable and uninterrupted view of the universe. While peering into the distant corners of the universe involves navigating light years, it also entails a form of time travel. The JWST utilizes infrared instruments to observe celestial objects and events dating back billions of years. The light emitted by these objects, due to the expanding universe, undergoes redshift, shifting from the visible spectrum to the infrared wavelength or longer. Fortunately, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling scientists to study the birth of stars, explore galaxy formation, and investigate exoplanet atmospheres. Its most recent groundbreaking discovery involves detecting an inconceivable mass of galaxies at the edge of the observable universe. This finding challenges the validity of the Big Bang theory, prompting a reevaluation of our fundamental cosmological assumptions. To better understand how we reached this point, let's take a brief journey through the history of space exploration. Early civilizations such as the Greeks and Chinese laid the groundwork for understanding planetary motion by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the early 20th century, Edwin Hubble, an influential astronomer, made groundbreaking discoveries in cosmology and observational astronomy. His observations revealed that distant nebulae were separate galaxies far beyond the Milky Way, transforming our understanding of the universe's size and scope. Hubble's law, established by him, indicated that galaxies farther away were moving away at higher speeds, providing evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race, with the Soviet Union launching Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969 as pivotal achievements. Fast forward to 1990 when the Hubble Space Telescope was launched, providing unprecedented clarity and breathtaking insights into the universe. The journey from ancient observations to the technological marvels of the James Webb Space Telescope showcases the continuous evolution of our understanding of the cosmos. It uncovered the vastness of space and transformed essential ideas in astrophysics. Take the Hubble Space Telescope, HST, for example. It snapped the famous Pillars of Creation image in the Eagle Nebula, revealing a star nursery formed by gigantic columns of gas and dust. Another noteworthy feat was the Hubble Deep Field, capturing thousands of galaxies in what seemed like an empty patch of space. The HST also delved into exoplanet atmospheres, pinpointing elements like water and organic molecules in distant worlds. hinting at the possibility of habitable zones beyond our solar system. Tracking the evolution of the nearest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These accomplishments solidified the Hubble Space Telescope's legacy as a cornerstone of modern astronomy, captivating the world with its astonishing cosmic discoveries. Its successor, the James Webb Space Telescope, JWST, was launched to build on technological progress and lessons learned from Hubble. An example is our understanding of the universe's beginning, which today is explained by the prevailing Big Bang theory. Around 13.8 billion years ago, the universe started as an intensely hot and dense singularity, rapidly expanding and giving rise to matter, energy, and fundamental cosmic forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the diverse structures observed today. The Big Bang theory also accounts for cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Although widely accepted, the Big Bang theory faced skepticism and challenges early on. Alternative models like the steady-state theory proposed a universe without a singular beginning, and concerns about evidence supporting the initial singularity, the expansion mechanism, and observed phenomena arose. Yet most objections were addressed over time. A pivotal piece of evidence came with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, along with telescopic advancements, further supported the theory. Precise measurements of cosmic microwave background radiation aligned remarkably well with theoretical predictions. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can peer through cosmic dust clouds. Operating primarily in the infrared spectrum, the JWST captures the faintest, oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to study star-forming regions, stellar nurseries, and the birth of stars obscured from optical telescopes. Infrared light, with longer wavelengths compared to visible light, penetrates interstellar dust clouds, overcoming a limitation of the Hubble Space Telescope. JWST can observe cooler objects emitting primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths, redshift. JWST's infrared capabilities detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Energetic events like black hole formations or new star births emit predominantly in the infrared spectrum, further expanding JWST's exploration capabilities. The telescope can explore phenomena that are otherwise hidden or invisible. JWST complements optical telescopes like Hubble by having enhanced sensitivity and the ability to detect infrared radiation. This capability allows it to peer farther into space and delve deeper into cosmic history, revealing concealed cosmic wonders and providing a more comprehensive view of the universe's evolution. The JWST serves as our window into the earlier stages of cosmic development. Recently, it uncovered something so astonishing that it may prompt a reconsideration of the entire cosmological model of the universe. We've discovered vast masses of galaxies at the very edge of the observable universe. These ancient galaxies existed just a few 100 million years after the Big Bang, nestled at the cosmic dawn. The puzzling part is that we're uncertain about how such massive structures formed so early in the universe's history. This discovery may lead us to reevaluate our understanding of the formation and evolution of galaxies in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic origins. JWST can gain insights into how galaxies, stars, and planetary systems emerged and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main constraint was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe. where these wavelengths are absorbed or distorted by cosmic dust and gas. The James Webb Space Telescope represents a transformative breakthrough in observing galaxies from the universe's infancy. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Leveraging its infrared sensitivity and advanced imaging capabilities, JWST has revealed a wealth of ancient galaxies, offering unprecedented clarity and detail in understanding the universe's formative epochs. Preliminary outcomes from JWST observations have stirred ripples in established cosmological models. The detailed data challenges some aspects of prevailing theories, prompting cosmologists to reevaluate fundamental principles governing our understanding of cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST's observations uncovered a higher number of galaxies in the early universe than predicted by existing models, suggesting a more complex and rapid formation process. Some observed early galaxies appear more evolved than anticipated, challenging conventional models predicting slower development. The detection of an inconceivable mass of galaxies challenges the presumed distribution and arrangement of cosmic structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and avenues for further exploration. The presence of massive structures challenges early models of cosmic structure formation, prompting scientists to refine models for a better explanation. Understanding how such massive structures assembled quickly after the Big Bang presents a puzzle requiring an explanation that doesn't violate fundamental principles of cosmology. Surprising discrepancies in the conditions of the early universe, compared to predictions based on existing models, have also been unveiled. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to reassess and improve our models of the cosmos. Currently, all we can say is that further research is needed to incorporate these unexpected observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses of the cosmos, but in-depth analysis sometimes reveals differences. For example, early observations might indicate specific properties or formations within distant galaxies that, upon closer examination, show variances in their composition, structure, or evolutionary pathways. To put it simply, cosmic phenomena are very complex and require careful analysis for us to accurately understand their true nature. Spectroscopy, a technique that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by cosmic entities. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and motion of celestial bodies. This analysis helps us understand the origins, evolution, and contribution of celestial bodies to the cosmic tapestry. The JWST has revealed numerous instances where initial observations differed from later analysis. For instance, initial observations of distant galaxies suggested an elemental composition primarily dominated by lighter elements like hydrogen and helium, in line with theoretical predictions. However, spectroscopic analysis using the JWST showed intriguing variations in elemental signatures, detecting heavier elements or compounds previously undetected or underestimated in the early universe. This challenges conventional ideas about the early universe's chemical makeup and the mechanisms responsible for their formation and dispersion across cosmic distances. Similarly, initial assumptions about galaxies in the early universe were drawn from preliminary observations suggesting a relatively uniform pattern of development and organization. However, more comprehensive investigations by JWST revealed a much more diverse and complex array of structural configurations within these galaxies. These differences have reshaped our understanding of evolutionary trajectories, implying that the mechanisms governing the form and evolution of galaxies in the early universe might be far more intricate than previously thought. On the other hand, the JWST has also confirmed several earlier hypotheses and observations. For instance, spectroscopic measurements by the JWST validated the presence of hydrogen, helium, carbon, oxygen, and nitrogen within cosmic objects, supporting theoretical predictions. The findings align with the widely accepted lambda cold dark matter model, which suggests the universe began with a Big Bang and consists of ordinary matter, and dark energy. However, since some predictions of this model have been challenged by recent JWST findings, alternative options such as the cold dark matter model are considered. This model proposes that the majority of the universe's matter is in the form of dark matter. This unseen matter, different from familiar atoms, does not interact with electromagnetic forces but exerts gravitational influence. The model aligns with our understanding of the cosmic microwave background radiation at the large or galactic scale. However, challenges arise at smaller scales, where discrepancies exist in the model's predictions regarding the internal structure of galaxies and the abundance of small satellite galaxies around larger ones. Another proposal is the quasi-steady-state cosmology, suggesting the universe follows a cyclical pattern of continuous expansion and contraction, challenging the Big Bang singularity. This model remains speculative due to its deviation from conventional models and the lack of direct observational evidence supporting its cyclical nature. The mirror universe hypothesis speculates about the existence of a parallel or mirror image universe running alongside our observable cosmos. This model suggests the mirror universe may have its own distinct physical laws and mirrored particles, offering an alternative explanation for various cosmic mysteries. However, it lacks empirical evidence or experimental data and remains largely speculative. The digital simulation hypothesis proposes our universe could be a sophisticated computer simulation. Proponents argue that our reality might be an intricately programmed simulation, similar to a highly advanced virtual reality construct. This idea stems from philosophical considerations and faces challenges in providing empirical proof or disproof. Lastly, the multiverse theory suggests the existence of multiple universes, each with its own distinct set of physical laws and properties. Our universe is just one among an infinite set of universes, each with different constants and possibly dimensions. While intriguing, we can't directly observe or access other universes, making it speculative. While alternative cosmological hypotheses may not be as widely accepted as the lambda cold dark matter model, it's essential to remember that even the latter faced skepticism early on. Confirming or refuting these speculative theories is challenging, but they might be considered if our present cosmological model fails over time. Recent revelations, though eye-opening, haven't refuted the Big Bang theory, according to many experts. Instead, observations from the James Webb Space Telescope have enhanced our understanding of cosmic history, aligning with predictions of the Big Bang. Massive galaxy clusters at the farthest reaches of the observable universe suggest gravitational forces were at work even in the early universe, consistent with the Big Bang's predictions. The presence of these massive structures at the edge of the observable universe implies their light has taken billions of years to reach us, offering a glimpse into the universe's past and supporting the theory's predictions about its evolution. However, these observations also introduce discrepancies that demand unbiased scientific attention. The JWST has opened new vistas, allowing us to explore the ancient realms of the universe. With the JWST, we confront a cosmological landscape teeming with new questions and intriguing possibilities. These uncertainties challenge established cosmological paradigms, prompting a re-evaluation of our understanding of the universe's birth, evolution, and fundamental principles. In light of such revelations, it's crucial to remain open to reimagining our cosmic narratives. These recent discoveries are but a prologue to the ongoing saga of cosmic exploration, urging us to continue our quest for cosmic truths through further research and continuous innovation in the cosmological arena.